All right,
Before I
everyone.
get started, can
Sure.
everyone see the slide? Is it the
I
right
can see
slide?
it.
Yes.
It's
Okay,
perfect. Yeah.
perfect.
Hello, everyone. Welcome to the December 10th edition of our Wildfire Resilience Seminar Series. Today, we're honored to host Dr. Michael Gollner from UC Berkeley. Michael arrived at UC Berkeley not too long ago, I think in 2019, from University of Maryland. And Michael is a preeminent researcher looking at many aspects of the wildfire problem. He has studied how fires ignite and spread within the wildland-urban interface, the physics and dynamics of wildfire spread, and he's credited for identifying several new mechanisms, unknown mechanisms of wildfire spread there. And he's looking at also emissions and health effects. So, like this multifaceted problem, Michael has an interest and threads of work on multiple aspects. Michael's work is well funded by many agencies, including the U.S. Forest Service, the National Science Foundation, NFPA, NIST, FEMA, you name it. And he's got really some excellent publications in the area, and I've read quite a few of those. And his work was recognized by several awards, including the prestigious NSF Career Award, the SUGI earlier Career Award by the Combustion Institute, to name a few. So with that, I yield the floor to you, Michael. You have the reins.
Thank you so much, ET. I'm really pleased to speak with all of you today and very excited about the topic. So, my background, I was trained, I went to undergrad all the way through grad school and UC San Diego. And, my background, I was trained in sort of combustion fluid mechanics theory and very much done experiments most of my career. And so, the range of topics is interesting, has moved over time, and I'll talk a little bit about that story. But it all fits having moved back to California, my home state, and tackling the wildfire crisis, where really this all comes together, and trying to apply some of the physical science sense of where my training was. And really, it's all led me to get more and more applied in many of the issues because we're missing so many of those tools necessary to reduce risk. So I want to give first a little overview. I moved, as ET said, it was actually in January 2020. So I had a good about 2 months before son got pneumonia, everyone got sick, and then the world was shut down. Pretty weird experience moving into this, but throughout it all, the lab is up. We're burning. The last hood that was planned to come online in March 2020 is now online at the end of 2021. So we're burning, our servers are up, and we're studying. A lot of the work I've done is related to Wildland-Fire. We've had a long-standing collaboration with the Missoula Fire Lab on how wildfire spread. I started a lot of this work when I was faculty at University of Maryland. Actually, most of the group I collaborate with are Berkeley alum there. That was never the intention, but there's this old clique, and it's been really great coming here. And we've tried to expand a lot into wildland-urban interface because there's just not a lot of knowledge. And that's going to be the talk today, talking about embers and how they ignite, and a little bit about how we take our spread modeling, which is currently for wildland, and Nagar and others on this call probably know even more of this from the post-earthquake fire community, and spread through communities. And I'll talk a little bit about the early stages of how we're thinking about linking this. And I know there's a lot of work and like to share. I'll also just mention some of the other things that the lab is doing, primarily experimentally. We're doing a lot on fire emissions. So we look at both the aerosols and the effluents and have started more gas sampling. I'd say our expertise is in understanding how changes in fire, the combustion side, influence those emissions rather than figuring out 1,000 species from a single fire. A lot of that's looking at masks for firefighters, which we started before the pandemic, and also firewalls. We've been doing a lot of oil spill cleanup research in that area, and spacecraft fire safety, which I started to get involved with before moving, but once moving to Berkeley, there were already some ongoing projects. And so we work heavily with low pressure flames modeling microgravity fires. I think one of the coolest things is the synergy between these. And just when we were talking about cleaning up oil spills the other day, we said, oh, did you know these certain things that they use in wildfires? And everything sort of connects. But wildfires are a key concern here in California. And I think we all know there's an increasing cost of fighting these fires and the destruction from the fires. Here I'm showing the actual area burned. An area burned probably is not the best marker, but it gives an idea of the extent of fires. What you can see in black is actually that the area burned from fires has been dramatically increasing since 1985. Before 1985, they track things differently, so it's very hard to compare. We probably were burning somewhere near this acreage 100 years ago, but at much lower intensity and much smaller number of fires. The problem that you see is that the number of fires in blue is almost going down or staying steady. Yet at the same time, the area burns going up. This is caused by 2–3% of the fires, which are blowing up dramatically in size. And that's where a lot of the destruction comes from, is that a small number of fires get very, very large, completely overwhelm resources. And sometimes they grow very quickly, especially at night, and that can cause major safety hazards. And of course, the suppression costs are going up, but suppression costs is a small fraction compared to destruction and other health costs. California has a history of fire. I'm just showing I was a part of the original Wildfire project through UCSD. On the left-hand side, you can see this is all the CAL FIRE collected data from 1878 to 2010. Lots of fires. A lot of the state is fire adapted. It's always had fire. Between 2011 to 2021, if you just look at the squares, you can see something. It's not just so much about the area, but it's that a lot of those fires on average are much bigger. And it's shifted where San Diego was sort of the center of the things in the early 2020s. Now in the later 2011 to 2021, Northern California has had more and more of these very large fires. Southern California too, but Northern California especially. And you can see a lot of the losses that have resulted. And it's really these WUI losses, which you can see here, which are just dramatic. The Camp Fire, the NorCal fires, which included the Tubbs, the Nuns, and the Atlas Fire, you know, just the number of structures burned in fires. California is winning that race, unfortunately. This is a nationwide problem, but it's very much concentrated. We just have so much wildland-urban interface and so many people here in California that we're losing a lot of structures. And the costs are in the tens, 20s of billions for some of these fires, and the deaths, of course, which most of which occur during evacuations. So it's a huge problem to tackle. And unfortunately, nothing's going to say it's getting better anytime soon. I like to say that there's three main drivers of change here. The first being climate change, which we know changes weather patterns, and there's more drought, more extreme fire weather. Fire exclusion, we've taken fire off the landscape, so the only time the fires burn are when it's the worst case scenario. We've had a lot of suppression, we've removed indigenous fire, and you know, we wait till the worst case scenario when we can't put out small fires. And finally, expanding wildland-urban interface. A great example is the Tubbs fire. There was the Hanley fire in 1967 or something like that. And it affected, you know, exposed some hundreds of homes, and there were only some tens that were lost. But the Tubbs fire, by that time, there were tens of thousands of homes and over 8,000 lost in that fire. So there's that change in time. There's more people, there's more power lines, there's more things being affected as well as ignition sources. So all of these combined together, climate change is probably one of the biggest because there's just more high fire danger days to cause a problem. So the talk today was focused on risk, and really we have to talk about risk, we have to talk about modeling. And modeling wildland fire is a challenge in and of itself. There's a couple things up here on the board. Topography, we've known, drives fires. Wind and weather drives fires. Of course, the fuels and the ecology. But they all combine, and I think we're still struggling just to model fire behavior and to try to make it predictive. Because let's face it, we have trouble modeling weather as it is. Oh, it won't rain today, it rained. Or where's that hurricane track going to go? So we struggle with that size. And then of course, fuels and ecology, you know, standard fire behavior models have 40 fuels. We know that there's more than just 40 different types of fuel, that the fuel changes dynamically. There's a lot of poor inputs that come in, not to mention the flame dynamics. We're not even modeling the real physics of the flames. And so all those simplifications combine to give us sometimes decent modeling, sometimes poor. It's pretty good to tell us that it's going to go faster upslope and faster with a faster wind speed, but there's still some issues there. And then let's complicate it. What happens when a home starts to ignite? And I'll tell you right now, there's no wildfire model that I'm well aware of publicly that can actually move through the Wildland-Urban interface. There are some privately, and the way they do it are really varied, and they're all proprietary, but a lot is based on data, and it'd really be great to have this more open and to start to link these features. So I want to start, before we move into modeling, why are our communities burning? I think that's been a big question. How could this fire possibly, this is Coffee Park, which is sort of the poster child example of a suburban community that was leveled following the Tubbs fire. That fire, by the way, jumped over a multi-lane freeway and a field before it got to this community. Well, there's three ways we generally understand for fires to spread through the Wildland-Urban interface. First is radiation. And everyone thought that radiation was the big thing here, right? You have a separation distance, you have a height of flames. But if you actually calculate it, rarely is there a fire large enough to ignite a home from the main fire front. When you just look at the fuels, there are exceptions, and the campfire may have been part of this, where you had very tall torching trees right next to hoses. But usually there's a good amount of separation. And that's why we talk about defensible space. Move the fuel away from the structures, and you won't be able to get the radiative intensity needed. You need about 30 kilowatts per meter squared to ignite a panel of wood. Now, there's another way that fires can ignite, which is direct flame contact. And this happens often where a fire maybe moves through a field or grass or shrubs. Maybe it runs along a wooden fence post connected to a house and then ignites a fire. If you have a relatively small fire, but it is directly abutting a home and it's on the physical structure, it's hard for materials to withstand it, especially if you have enough fuel for it to last. So you put a wood pile right at the base of your home, and it gets into the eaves. There's little you can do about that, which is why we talk about the 0 to 5 foot zone, keeping flames away and anything that can generate flames away from next to the home. And then the real kicker is what actually causes most of the ignitions, embers or firebrands. And this is by far the biggest challenge to simulate. Small burning particles, which I've attempted to animate here, which land and then quite annoyingly will ignite a fire, not where you expect and not at the time you expect. It's a very complicated smoldering to flaming transition. And I'll talk a little bit about ignition from it. But you almost think of it, Jack Cohen always describes it as a blizzard of embers. Maybe that's a little too cold, but you can see this is the UC Davis Fire Department at the Tamarack Fire. Winds are whipping up and embers are blowing everywhere. They can get transported kilometers ahead of the fire. Usually it's a large cluster of them closer to the fire. But most homes at the Wildland-Urban interface ignite due to small flying embers, not the main fire. Investigations by NIST and IBHS and the UCANR have estimated it somewhere between 50 to 80% of the ignitions occur due to embers or indirectly from igniting something in the yard, which ignites the home. And so you can see on the bottom right, it's a great example. The roof of the structure is on fire and nothing around it is really on fire. It was not the main fire front. It was clearly an ember ignition on a roof that otherwise shouldn't have ignited. So how does it go from being a wooey fire to being a disaster? And so this is adapted from Kalkin et al. And really it's from Jack Cohen's description. What's that transition when we're igniting homes to making it level a community? Well, we have severe wildfire conditions. So high winds, dry fuels. This is key conditions for a fire to escape initial attack. So when we go to put out the fire, it doesn't work because it spreads too quickly. Generally, if flames are higher than the height of a 6-foot man, which is where these standards are based, we generally can't fight it by hand. And if a fire is going to be larger than that, it's going to be very hard for us to put a stop to it at any time soon. And so when you have high enough winds, you'll quickly reach that in 20 minutes or something. And then that fire is going to be too large even for aerial attack. Sometimes we can do a good job, but it's rare on those high fire danger days. It causes extreme fire behavior, which is large flames and high growth rates, and ignites residential fires. But here's where it changes. The fire department is, developed to respond to fires. The Tubbs fire was a great case where fire resources were called, and within an hour or less, it became impossible for them to respond to these fires. And so what happened is they became so overwhelmed, they transitioned. And I'm told by the CAL FIRE chief that was there, this is the only time he's ever heard this over the radio. And he heard it later after that incident. But this is the first incident where he heard that there will be no more response. There is no more backup, focus on life safety only, and just try to get people out of there. There will be no structure protection that evening. No one will arrive till the morning in the sunlight. And those resources becoming overwhelmed diminish effectiveness. NIST studies have shown if there is a fire truck parked at your house, that is a best protection because there's a small fire and they're going to put the water on it. But embers mean that thousands and thousands of homes are exposed at the same time. And this fire may move like the campfire moved in a matter of an hour or two and engulfed a town. There just simply is not time to move those resources. So we have to do mitigation in advance, or we're going to keep having hundreds or thousands of homes destroyed. And, how do we make a difference? Well, there's a couple ways. We can break this chain by reducing exposure. So instead of having extreme fire behavior, if we better design the community not to be adjacent to an area with extreme fire danger, if we do fuel reduction treatments around, if we do prescribed fires at regular intervals, all of these things can lower that intensity. We don't remove fire, we simply lower the potential intensity that is then going to be imparted on the town. It's a little different than the earthquake field where earthquake's going to happen and we have no control over the jolt. Here, if we design the area around or we manage it properly, which can be its own legal hurdles, then we can actually reduce the exposure. We can't make it zero, but we can reduce it. The second, of course, is to harden our structures. We call hardening as making them harder to ignite and harder to spread. There's the Chapter 7A of the California Building Code, NFPA or ICC codes. There are community programs like Firewise, which focus more on defensible space. All of these combined together can help make it so that it's not that a structure is unignitable and unburnable, but it makes it less likely that they're going to ignite and burn. And finally, we can improve response. And as much as I say we have to focus on mitigation before, preparing the response is still important. What about notification and evacuation? These are absolutely key, and most people are dying in these fires during evacuation rather than being trapped in their homes. And so the way we notify people, the way we track the fires, the way we track people and design evacuation routes needs a lot of work. It's not my area of expertise, but I work with others who are doing fantastic work in this area, and we really need more. So I'm going to focus on two things. I'll talk about the risk and modeling a little bit, but first I want to talk a little bit about experimentally. What happens when embers actually approach a building and ignite it? And I'm just showing, this isn't an experiment I did, but colleagues at IBHS, actually a former student there, runs a lot of their wildfire program. And you can see ignition here of a decking piece in front of a pseudo home. And so they're lofting these embers and seeing how they accumulate and then ignite that decking piece. So we've taken that scale way down and have a very small laboratory scale apparatus. And why do we do this? Because those experiments are great, but we never actually see the behavior of exactly how those little embers land on a material and actually ignite. And so we've done 3 or 4 different studies, mostly funded by NIST, that are looking at how different types of embers accumulate and then ignite materials, and what kind of heat fluxes do they provide? How long does it take to ignite? And that is key to us designing a proper protection scheme. And eventually, we'll need to put this into our WUI models. So I want to just recognize Hamed and Raquel, who are the graduate students who worked on this. So most of the experiments are going to use the middle set. We wound up using the same material that a lot of other studies have used, which is just These sort of wooden dowels, you get them if you're putting pins in for your IKEA furniture. And they're very repeatable. They're great because they're fluted. They get a nice ignition profile and start smoldering. We did do some tests, and I'll talk about the difference between that and some real firebrand materials. But all we have here is a wind tunnel. You can see it's wrapped up in foil because sometimes you drop little pieces, and a lot of our wind tunnel is 3D printed prior to the test section, so you don't want to melt through that. But the wind tunnel provides a constant flow over there. And it's been augmented now, not in the work here, but some other work we've been doing to actually do emissions diagnostics at the same time. So the initial studies we did on embers were looking at what's the heat flux that we get from this. So you can see example of different smoldering embers. And we chose not to use single embers because very few single embers can actually ignite a solid material. They'll ignite a bed of dried pine needles, but they won't actually ignite a piece of wood. Instead, there's an accumulation. And you see this in a fire, that in crevices and cracks and different areas, embers will fall and they will accumulate, just like leaves around a house. And so those same areas that accumulate leaves and stuff are going to catch those embers. Now, the leaves are its own problem if those are ignitable, but also as you build up those embers, it's going to change the heating profile. So we've chose a fixed amount of deposition of the embers, which you can see on the left, and then looked at the heating that's going to occur. And as one might expect, as we increase the wind speed on the embers, the heat flux goes up. You can see here it reaches about 40 kilowatts per meter squared in the center, which, as I'll show you, is plenty enough to ignite a piece of wood. The other interesting thing, which probably should have been expected, the more you increase the wind, the shorter the duration of heating. So there's this interesting balance because as you increase the wind speed, you're increasing the heating. Just think of blowing on your coals. But at the same time, you're decreasing the amount of time that there's actually available energy to heat. Now, this isn't a real fire where the winds are fluctuating and embers are depositing at random. We did all of it at once. But still, I think it holds that there's going to be a short window over which it's going to try to ignite a material, and it's either going to work or it's going to fail. Now, I mentioned, what does it take to actually ignite a material? And on the right, you can see a chart from Drysdale's fire dynamics book, and just go through, wood and other materials. Unfortunately, most of these, it's radiant heating, so not from an ember. It's on a cone calorimeter, and most of it's piloted. One column has an entry for spontaneous. So piloted if there's a flame around. We're somewhere between piloted and spontaneous because the smoldering embers are hot, but they're not quite as hot as a flame would be to ignite something. But let's just say you need spontaneous. We're looking at the order of 30 kilowatts per meter squared to ignite a panel of thick wood. Well, on the left-hand side, you can see the peak heat fluxes reached with wind speed very clearly go over that at a pretty moderate wind speed on the order of 0.75 to 1 meters per second. And so we have a serious problem where, probably as we knew, embers can impart enough heating to ignite the materials directly. And any range of sort of regular material can ignite from this. And so we need to look at more fire retardant or resistive materials in order to avoid ignition. Now, this may sound all wonderful, but the reality is changing materials on a home is really difficult. And we're not talking about, the main structure and taking wood out from the inside, but even if you have stucco, if you have one exposed wood member on the eave, which is very common, you are now creating an entry point. And this could be an entry point where things accumulate and things can move in. So it only takes one crack, one opening where this can get in and actually cause a fire. So it's actually kind of a challenging problem. Now, there were some questions after this. What happens of the firebrand material? So the bottom right, you can see we tried different sticks, we tried bark, we tried different shapes. Generally, there are some small differences, but at higher wind speeds, you start to see some small differences. They still generally are on the same order. The sticks produced something closer to the 40 kilowatts per meter squared that we were getting with the pins and dowels. Some of the pins and dowels were actually giving a little bit less in some of these because it was a different size. But there is a size and shape effect. There is, in this paper, we looked at some correlations with the way in which the pile deposits and how it sort of, starts to decay and the shapes. And there are some effects, but it generally is on the same order of what we were doing before. One of the biggest tells, of course, is how much, what's the mass of ember load that's landed? What's the density of the material that it's landing on? Because that plays a huge role in the heat transfer. And finally, what's the wind speed that it's affected by? And we can expect in most of these experiments, this is a super low wind speed compared to what you might see in a wildfire. We went back to that question as well of what's the difference between that single ember and that pile? And there's a lot of questions because everyone's focused on single ember experiments up until this point. And you can see the heating we got from single embers. This, by the way, is without wind. These spatial sensors didn't work so well with wind. When we did it without wind, you can look, instantaneous average peak heating, the heating from a single ember is incredibly low in comparison to what we get from a pile. And so we can surmise that a single ember is probably heating the material by contact. And yes, if you had a small pine needle that was directly touching something smoldering, we can move the smoldering front and eventually transition to flaming. However, in the bottom, once we have a pile, 10 grams of embers that are smoldering deposited on top, we can't very well rely on this single ember assumption. We're actually getting heat fluxes on the order, peaks on the order of 28 kilowatts per meter squared, on average 10 to 12 in the center here. It is spatially distributed and it's much higher. I think a lot of this has to do with re-radiation between the pile. It's something that hasn't been fully sorted. It's very hard to put sensors in something that is reacting and glowing and degrading your sensor and heating and cooling from your sensor at the same time you're trying to measure. And so that's still something we're trying to do, is to tease out the different mechanisms. The final measurement that we wanted to show here is related to ignition and heat flux in a crevice. And so all of the previous results were on a flat piece of wood, but I think many of us know that most of the ignitions in a wildfire aren't occurring on a flat piece. They're occurring in crevices, in decking board, they're occurring in little nooks and crannies in our wood roof. And so what we've done is we are looking here at pressure treated wood and redwood, two common materials used in decking. And we use a standard spacing, which is used for decking, on the order of a centimeter. And we looked at these igniting with different wind speeds and at different angles with the wind. What happens if the wind is blowing right through the crevice at 0 degrees versus across and over? And then we did all these experiments not only on the wood, but we also did these experiments with a sensor suite to try to look at the heat fluxes. And then we can compare that to the flat data we have. And I don't think we can get too much from the wood. Basically, whether it's pressure treated or redwood, if you crank the heating up high enough, you will smolder and eventually transition to flaming. And so redwood is generally considered a fairly fire resistant material, but if you give enough embers and you give enough wind, it definitely will ignite. Ignition in the crevice, though, is a lot more than that. And it was really fascinating to see when we try to measure the heat fluxes inside that crevice. And so on the left, the 0 degrees means that the wind is flowing straight through the crevice and aligned with it. And on the top right, I'll show you one that's about 30 degrees. So it's at an angle to show the biggest difference. And on the bottom right, this is flat with no crevice. And so with no crevice at the particular conditions we did, so we only moved up to 1.4 meters per second. We didn't go to the higher wind speeds, and I'll talk about why in a moment, that we did in earlier studies. It only reached about 20 kilowatts per meter squared. Well, at 30 degrees, we're getting near 40 kilowatts per meter squared, which is a substantial jump in heating. However, if we align the wind directly with the crevice, which probably isn't the most common wind situation, but we get a dramatic jump to the point at 1.1 meters per second, we're getting 75 kilowatts per meter squared of heating. that can burst into flaming rather than just starting a smoldering process. And so we see a really dramatic shift in a crevice, and it makes sense. The crevice or any kind of these nooks, not only do they capture the burning material, but they also aid in re-radiating the heat and causing it to actually heat the material greater. And so it's very dependent on the geometry, very dependent on the wind speed. But knowing that wildfires have such dynamic and changing winds, I think we can expect that over time, the wind speed will eventually reach this peak perfection where we're getting very, very high heating rates. And so it just tells us how important considering the geometry and considering everything else is, and that if we're going to certify a material in a flat configuration, that's not going to give us everything. There's still a change in the geometry. We can get 3 times the values and really blow all of our assumptions. And so there really is something to looking at how we can try to prevent ignition in crevices and just change some of our designs to try to prevent that. So I want to do a shift, and I know this talk is a little disjointed, so but trying to merge what we're doing experimentally. We've done other things on like generating firebrands, and I think just with the time, I think everyone's going to want to hear a little bit modeling fire spread and risk. And I'm really going to talk about mostly looking at the Tubbs fire. You know, what happens when we have the flames moving is that we have a wildfire model that stops right where this fire did during the Cedar fire. The fire didn't stop there, but at this image, that's where our models end. Once we no longer have vegetative fuel, we can't model into the urban community. When we think about risk in the community, if anyone's familiar working with wildfire, everyone loves triangles. And so we're going to see a wildfire risk triangle, which has to do with likelihood, intensity, and susceptibility. And the current wildfire hazard and risk analysis considers a landscape scale. We're talking about 30-meter to several kilometer size squares grids. I mean, the risk analysis was developed for a nation-wide analysis of wildfire risk. It was not developed with a community in mind. And so the work on community risk doesn't really include exposure conditions. And that's something that we've been missing and looking for. So on the bottom, you see there's a likelihood, intensity, susceptibility. We go to community scale, I think the susceptibility is going to be important to understand because we have to understand the exposure conditions. So long-term, we want to develop a WUI spread model, whether that comes out of the earthquake engineering literature, which I know Nagar has been working on and others, or something data-driven, or something physically based that's new. So when we're looking at risk in the WUI, we have hazard, the probability of a given exposure level being achieved. And so this comes a lot from previous weather data. What are the likely conditions? As well as for hazard, it's going to be the actual wildfire conditions that can be reached at those conditions, so the fuel models, and the vulnerability. And I'll tell you right now, the problem is vulnerability. What vulnerability do we have for homes? So we have very little, if any, susceptibility data of a structure to a given exposure level. So this was the beginning of a project that I'm going to show. It was led by a PhD student, Raquel Hakes. She's now a postdoc at Sandia. And so she worked in her thesis on a reconstruction model methodology. So we have a great database of structures that have burned in fires. And folks have published papers, Alex Sifford and others, that have, and John Keeley have looked at, okay, structure burned, what was the fuels nearby, what was the weather conditions, what was this? But I'm really interested not just in that, but what was the actual exposure of the fire to that structure prior to it burning, as well as what were the conditions? And no one is there collecting that data. So we want to fill it in by trying to run those wildfire models of those past fires, match them as best we can, and then pull out things like the flame lengths, the rate of spread, the fire line intensity, and of course, embers. And that's probably one of the hardest parts. And so that's the goal of what we've been doing, is to try to recreate fires, take the loss data that's been collected by CAL FIRE over the years of all the structures that have burned, try to fill that in with the structures that didn't burn, which they weren't collecting, and then try to do an analysis and see what factors are actually important, and can we look at this in a data-driven sense of modeling fire spread in the future. So this is the Tubbs fire. It was the second most destructive fire in California history. It's maybe dropped down the list a little bit, but it destroyed 5,600 structures. There are more outbuildings as well. The Nuns and the Atlas fire were also going on during this time, but you can see how it burned through the Coffee Park community and really went through suburban, but it also started up in the hills and went through a rural community. So it's a nice fire. It was very fast. In 5 hours, it burned to Santa Rosa. Unfortunately, we have very little information about the fire as it went, but we know the final fire lines and we know everything it destroyed. And it destroyed both rural and suburban, so that gives us a nice starting point. So the validation, so we ran these models in a model called Elm Fire. It's very similar to Farsight, which is the current landscape scale model of choice by the Forest Service. Elm Fire uses the same Rothermel type, which is a 1D correlation for flame spread that the Farsight and FlamMap and every other US model uses. The difference really is just the way it was developed by Chris Lautenberger, who's now at Rex Engineering. He's a Berkeley alum, and basically it treats the every fire run probabilistically from the beginning in a level set context. This helps us in the analysis and in terms of developing everything for risk. It also has a better treatment of embers. It intrinsically has a probabilistic treatment of embers. If you ever dig into Farsight, Farsight only lofts a single ember from a cell to another single cell. That's all it can do. And so it's a little bit limited, and it only does maximum lofting. It doesn't do in between. And so that's why we chose to switch to Elm Fire, is it just treated things better when we were looking probabilistically, and it already had some of these ember models and the links to WRF and other models we needed built in. And so doing this, we do a decent job of remodeling the fire, but you can see it misses some features. It misses the backing fire. It misses a piece of the eastern flank because there was some kind of outward flow that is just never picked up by the weather model. And finally, it misses the urban community. Now, this is a fault, but this comes back to the point that fire models don't spread in urban areas. So that's okay, because instead, we're also looking at the ember cast on the left. And what you can see is that the embers were cast far beyond this fire, and this is probably a relatively realistic ember cast. So there's more embers cast in the center of the fire, but it does move into the urban area. And there's only a small area of the urban that isn't covered with embers, and that's probably because it was a totally suburban fire and it was spreading relatively slow until the winds died down. So what we try to do now is to link that with the exposure level. So we have both embers and flame length, and on top you can see the fires. We have green undamaged structures, yellow damaged structures, and black destroyed structures. There are very few damaged structures, just the way that they collect it and just the way fires behave. If there's nobody there and an ember gets in, it might take 10 hours to burn, but that house will burn to the ground. Houses are designed to have a fire crew come and put out the fire. And during an event like this, there's just no one to do that. So only about 10% are damaged. Most of them are completely destroyed or they're unharmed. So looking at the exposure levels, I mentioned, what happens in that urban area, and Coffee Park was sort of the poster child. The flames don't readily expose the urban areas, and you can see the flame lengths here, but it is actually included in the ember cast. And so most of this area receives, it's actually interesting, a very low level of ember cast. So there's definitely embers that are lofting. Remember, the ember model depends on the distance from the source, the intensity of the fire that's generating, as well as the wind speed and direction. And so it's lofting those embers in this area, but it's at a lower density. But it doesn't take a big density of embers to ignite a fire. So once that fire gets going, it then became an urban conflagration and spread through the area. And we sort of missed some of the ember exposure further down to the left. So what we try to do is try to take this sort of fragility curve approach as a first take. So we're fitting the fragility curve with a general model. and we find a response variable for each structure and basically whether the damaged state. So we took basically everything that's undamaged, damaged, or destroyed and go between 0 and 1. We didn't really look at the damaged because damaged structures were so small, and so we just sort of lumped them within destroyed. And that seemed to work better and to simplify the analysis a bit. And it was a small number of structures in comparison to everything else going on. So now looking at the fragility curves. So one thing you'll notice is it doesn't go to 0. That's something we've worked on. And one of the reasons is we haven't teased out yet. There's 2 different curves shown here. One is the ember level, right? And so embers are exposing. But there's a lot of places that have both ember exposure and flame length exposure. And so they're dual exposure. And it's hard for us to tease these out. It's also hard for us to tease out the structure to structure spread, though we're working on doing that now. And I think we'll see this come down and change with time. But even on an initial take, we can start to see some interesting trends. One is there's a 45% increase in likelihood of ignition from no embers to severe. There's definitely a change with embers, and it's most significant in those areas that are not affected by the flames, that are more in the urban areas. And if they're within an ember exposure area, it really does make a huge difference. The second is there's only a 20% increase depending on the intensity of the flame length, which sort of is telling us if there are flames near the structure, there's generally a higher risk that structure is going to be destroyed. Now, this is not telling us as much about the local area. We'll get into the defensible space in a minute, but the embers have a much stronger signal in terms of the likelihood of destruction. Another interesting point that CAL FIRE was most interested in is what's the effect of the code changes that occurred in 2008. Now, this maybe isn't the best fire to test this because the homes that were destroyed, it was one heck of an exposure for most of these homes. So actually the homes in the lower end were less than others, but we do still see, separating the 2008 versus the pre-homes, a 10% decrease in destruction probability. And 10% doesn't seem like a lot, but considering we don't account for did you maintain defensible space or anything else, there still was a significant decrease in the probability of destruction by having the newer home. Was that newer home just because it had the code changes or anything else? That hasn't been teased out, but it's something we continue to work on. We'd all love to have data on all of the structures prior to the fire, but we're sort of limited by what a Google truck running by or what satellite data was taken before the fire, since they didn't have pre-inspection. They are doing more defensible space inspections now, so that may change with future data sets, and we may be able to tease this out more. Now, speaking of defensible space, this has been found to really be a key influencer. So we've looked at the effect of defensible space, and we looked at how this changes probability of destruction with embers, because embers were most sensitive. The 5 to 30 foot zone, there was only a 10% change with intensity level. However, in just the 0 to 5 foot zone, we saw a large change, nearly 40% change for some of these cases. And so there's a different behavior between dense and sparse vegetation. Now, this initial run was just basically looking at what's the distance from the home to the vegetation. It'd be very nice if we can parse this, and we're trying in terms of image processing from satellite to look at the density of vegetation. It's always hard after the fact to really understand how coherent was the vegetation getting up to the structure. But eventually, we're just going to have to rely on large data sets to be able to parse this. But it does seem that that 0 to 5 foot zone plays a very large role in whether the structures have an increased probability of ignition. And it makes total sense from what's been seen in the lab. If you have small materials near the home, it can spread up and the flames can move inside. So I know I don't have full conclusions. This was a project done mostly during the pandemic. Absolute disaster for many reasons on many sides. And we're moving, there's a lot more that's really not ready to show, but hopefully we're going to have some really great data. I'm showing a picture of Greenville California, which was destroyed in the fire. You know, just to highlight, it's not just suburban communities. In this case, this is a rural community and the entire lifeblood of the town is gone, much like Paradise was. Although here, reporters were actually in the town while it burned. And so there's really a key need for us to take these communities and make them more resilient to fire. So I think key takeaways when I'm speaking with engineers is to remember wildfire is a natural ecological process and we're disrupting it. And our goal is not to remove fire, but reduce risk and to make it so that our communities are going to survive. We can lose a few houses, but we don't want to lose lives and we don't want an entire community to burn. We want to make the community resilient so that a few houses burning isn't going to take down the entire community, which in many cases under extreme fire conditions is the case right now. So as engineers, we're trying to create models and optimize and prioritize decisions. We need quantitative experimentation and understanding of the process. I'm always a bit skeptical of proprietary solutions that aren't vetted. There's many unknowns still. And all the models that I have found and information are mostly in proprietary literature. And so there's a lot of things missing that we really need to get out in the community. And of course, these models don't move from wildland into WUI, and there's little validation data. We don't understand all the physical processes. And so it's critical that we keep moving in that direction. What happens if we can model that? Well, I think beyond insurance's obvious interests, what if we could make direct recommendations? Should this community, should they change their roof? Should they do more defensible space work? Should they change their vents? Should they change their window? Who should change? Only on the outside, on the inside? What's the best arrangement for homes in the community? How many homes, this was a question actually from the state legislature. How many homes in the community do you have to protect till it provides sterilizing immunity for that community, which is clearly a pandemic term they're learning about, sterilizing immunity. And I don't think anyone knows. And I think it definitely depends on the exposure. And so it's all sort of a mixed thing. Now, if you guys know Charlie Scawthorne, who's up here at Berkeley, he's big in the earthquake field and he has lots of opinions on things to said and would love, we want to move to a physical modeling approach, but initial attempts at trying earthquake models with fires have been difficult. And I think Nagar probably, I'd love to hear her opinions because she has a recent paper on this. But building something from scratch, there's a lot of aspects that go into this. And at least in my expertise in the firebrand models, we don't even have a lot of the numbers to do this accurately. And so I think there's still going to be a lot of data-driven pieces that need to come in to make it work before we can move to a fully physical approach. Because we still have a lot of unknowns even in the physical processes. And so I hope out of this you get that embers can deliver the ignition heat fluxes. It seems totally obvious to me, but there were some questions in the community maybe 5-10 years ago when we started, and that we have to look beyond a single ember and how clumpings of embers. And hopefully we can start to develop this relationship between exposure and destruction. And, practically just the fact embers and flame length are going to behave differently for risk. And we only need a few embers in practicality to take down a community if the conditions are right. And so we really do need to look at how that exposure changes, and hopefully we'll have some field data to start to link some of these pieces in the future. So that's all I have, and I'd love to take questions and comments and any discussion from the group.
Great. Thank you, Michael. So let's hear it from the audience. Any questions I may direct? Okay, someone raised a hand. Pega.
Thank you so much. Thank you for the presentation. I actually have a question related to one of the slides that you showed at the start of presentation. In terms of burnt area between 2011 to 2021 compared to before. And you show the trend of reduction of, this wildfire from south of California to, goes higher in north side. So I'm wondering what are factors that cause this, changes and,
Yeah,
reduction in the south part. Yeah.
it's a great question. I mean, I'm not the weather and the fuels expert, but from what I've learned from them, I think in terms of the way that we respond, SDG&E, when I was still in grad school back in the day, was acutely aware of this issue. They started upgrading lines. They started their own power shutoff program early. San Diego County, they've still made some mistakes, but they did significant work in reducing fire risk. So I think Southern California had an earlier hint and started to work on things a little bit earlier in reducing risk. There are still issues. Some of it has just been Northern California has been very unlucky. We had those lightning fires, which ignited fires in areas that haven't had fires in 50, 100 years. We've had a lot of Diablo wind events, a lot of those phone winds, and Southern California hasn't had as many. So there's some climactic regions, and I think especially further south towards San Diego, where we had the Cedar Fire and the later fires from that, you could see the firestorms that came later. The destruction wasn't at the same level despite high fire danger conditions. So I do think they learned a bit from it. I think in Northern California, it's been a little hard. Lake County, I think something like 70%. I can't remember if that's correct, but it's over 50% of that land has burned, and a fair percentage of it has reburned in just the last couple of years. And so it's just dramatic, the drought and the weather conditions up here. So it's a combination of factors, I think.
Thank you.
Brian?
Yeah, thank you very much, Michael. Very good presentation as always. I was wondering if you might comment on kind of expanding this idea of the challenge of having, multiple embers and orientation of the decking material, for example, and how that increases the severity of the damage, and scale that up to a community, because depending upon how you have orientation of buildings and orientation of streets and distances, perhaps there could be, some factor there in, the probability of more of a wide scale destruction in the community. So just would be interested in your thoughts on the extent to which that might be considered needed to be looked at as we look at kind of the WUI disaster potential. Thanks.
Right. Okay. Well, I would say in the crevices, I think what we're looking at probably has most application to test and small scale design standards. So we're not going to change the orientation. Who knows how the wind's going to come? Because the wind, we may know where it's going to come, but it's going to flow around the house. It's going to do things. That's not going to factor into the design of a deck. What we can say is that inside that crevice is really hot and a key area for ignition. So there should be no way for things to catch in there. Does that mean that we need to add a coating on the sides of the beams? Will that coating last for 10 to 15 years after foot traffic? That needs to be done. Can we put a piece of metal flashing on the underbars? Will that be enough to prevent ignition to spread? We know the flames can spread and smolder through. There may be a simple enough solution for certain designs that we could put flashing in certain places and it would prevent embers. I mean, you might get a small fire, but it wouldn't be able to propagate to the house. And so it's those kinds of small solutions which might be a compromise enough. Now, it's pretty hard to put that in after you install the deck, but it works for new decks. In terms of community design, yeah, I think embers are going to be flying, and I think that there's going to be wind patterns that are very interesting and expose some structures more than others. And we just have no idea. Probably a great opportunity for modeling. We're never going to get that data in the field. We can't even get good wind data for a flat fire in a field. Like the Eglin Air Force Base prescribed burns, they have like 20 wind sensors, and they're all different. There's so much going on in the atmospheric boundary layer. But you get a few point measurements in the field and you really compare with modeling. I think we could learn a lot about the flow in the community, and that might influence our design decisions. And I think we could see these types of effects between structures. We don't know how far to space our structures. We don't know. They say 30 feet in the code or 15 feet with sprinklers. No justification for that. There's a lot of unknowns. IBHS, CAL FIRE, and NIST are working on some of the questions, but there's a lot to do.
Negar, go ahead.
Thank you. So thank you, Michael. Great presentation and very, very interesting discussions. I very much enjoyed it. So quick, perhaps follow-up comment, acknowledging what you mentioned about post-earthquake fires, followed by a quick question. So yes, you're absolutely right with post-earthquake fire models and work of Charlie Scothern. I think the primary difference there is that after earthquake, we get a few ignitions across the community, but they could be far from each other. And then they start individually and could spread. So the problem is not simple, but it's simpler than or different than the wildfire problem, because then you can somewhat simplify and look at fire spread in an elliptical shape, how it spreads, out from that individual structure. Whereas here still there is a line of fire involved because you got a series of structures ignited all at once, and not even in line because you got the spotting, so you can have multiple lines going on across the community. So that makes it, and we indeed looked at it, and if you want to apply, because some of the versions of models for fire following earthquake that are out there, if you apply them to these WUI concepts, what we get is that they underestimate. Some of them they're data driven and they did include a wildfire WUI sort of data, but from old days. And if we map and use, for example, Santa Rosa, Campfire, these fires, they significantly underestimate the fire spread rate. So it's not expandable. And then my follow-up question is, so the plots you have where even if you have non-category for the severity of the spotting or brands, you still have a probability for damage, right? It starts with 0.4, 0.5. You mentioned that it doesn't start from 0. I wonder, yes. I don't know, I could be totally wrong, but I wonder, right now the spotting and the ember level is coming from the simulation is capturing ember level only in the wildland, right? But there could be also, if we have these, now we move into the community and you have now houses on fire, they also now generate embers, as well as, they become fuel themselves, which could be, you may know in the non-category actually, because you have now embers that are coming from a different source.
Right. Yeah, and so we're really, so there's two sides, so we're skipping the structure to structure component, and we have found, and I don't have updated plots, but it probably goes more to 10 or 20%. It really changes in left hand. When we get a better capture, there are other structures that weren't exposed that are not part of any of the databases. And as we've manually started to enter them, the curves have looked, the data hasn't changed, in any of the results, but we've been better at moving that bottom probability down because we're getting more structures that don't have exposure. So that is helping. One of the things that is going on is that, eventually we'd love to use this so that we can do it with current wildfire models and base it on what we have. And so, I think, one of the keys basically is that embers is just so important here. The urban fire spread is important too, but I almost think that getting the ember model right and coupling that to the risk might be just as or even more important in how it's driven. And right now we sort of just pick, in California, embers are 1 kilometer out or 2 kilometers out, and that's our distance. We need to do better than that. And just starting with a sensitivity study hasn't even been fully done and captured. And so I think that's a lot of area to improve. I really appreciate the comment on the multiple ignition sources. That's interesting. And in some ways, that's what embers do, but on a scale that's just totally different. And it also creates interacting fires and wildfires that are difficult to capture. And how it works in the suburban community, I have no idea. I wish someone had an IR camera aimed at a fire. I wish we didn't have the fire, but I'd love to see the data. Yeah, so
Great.
I don't know if that answered all the questions, but
Definitely. Thank you.
I see Jean raising her hand. Jean?
Oh, I can't hear you, Jean.
You are unmuted, but somehow I can't hear you.
Hello? Or maybe type if it. Oh, uh-oh.
All right. Okay, so maybe while Jean is typing her question, I can ask a question in the middle. And this is related to the slide you were showing about the fragilities, Michael. So in earthquake engineering, we have intensity measures that we use, and there are two kinds. One kind is the amplitude-based intensity measure, like what is the peak ground acceleration that happens instantaneously during the earthquake, etc. And then another one is duration-based. And the duration-based, like RES intensities, etc., are good for gauging the fragility of structures that are vulnerable for like extended exposure during the duration of the earthquake is as important as the peak acceleration it can induce. Have you thought about things like that? You're thinking about flame length, but how long is that flame at that height is lasting? Is it like microsecond? Of course, then it's not going to cause anything. So obviously your data kind of aggregates a lot of stuff in it, but was there ever a need to think about the duration-based metrics to characterize fragilities?
I honestly I haven't thought about that in this context. We've definitely thought about it in the heating context, and it's a little unclear. For the ember heating, wood does this funny thing where it chars up, and if you don't get it quite to the point to ignite and it doesn't spread too much from where it started, that char layer starts insulating it, and so it tends to not always be as high of a risk. But winds can change later and things can still happen. But for the duration from flaming, I haven't thought about that. That's something that could be pulled out of the data and looked at, but we haven't tried that before. That's an interesting way to try it, because we could estimate not the change in intensity over time, but we do this for emissions calculations of how long the flames are burning before it gets to post-frontal combustion. And so that would be a correlation with the fuel type, which we could play with and be interesting to see.
All right, so let me just recite Jean's question here. Jean says, I wanted to say I really like the Ember model. Also, I had a question about the fuels. Have you looked at aging of the deck materials? I understand the need for building codes. However, most checks are in significantly worse shape. So
that's true. They're often in worse shape. I haven't very much in my own lab. IBHS has done some aging studies. They particularly did a lot on roofing. They also did some really interesting studies on both intumescent, gel, and some other fire retardant coatings on materials. Basically, you age it long enough, which doesn't have to be that long, and the fire retardant coatings don't work very well over time. for the ones that they tested, which of course they don't mention the brands. I haven't tried older deck materials. Doing an aging study or getting it is hard to do, and usually my funding in WUI comes in 1-year chunks, which has been a long-standing problem. We start a project, we have to end a project, and then it starts up again 7 months later when funding is available, and then trying to get someone. So a lot of those Ember projects too, we've been very lucky, and I'm grateful for the funding, but they've never come continuously. So it's always come in chunks, in rush, as things become available, because there isn't a good dedicated program. And so long-term stuff like that would need more long-term study. I think IBHS will study more things like that, but I'd love to see a key way to just prevent that deck from getting out. And some of the testing that they do in California, fire marshal testing, Steve Quarles showed me a lot of the data and how they do that. He used to work at UC and then at IBHS, and is retired now, Marin County, but they lob fire at a deck and everything chars. And some materials will almost burn out and be charred, and then they'll survive the rest of the fire input. But those decks are actually quite flammable. It's just that the fire was so much it charred it and created a char layer. So those tests aren't necessarily representative of reality. And so I think that's where our Ember work falls in a little bit, is understanding that gap. And I'd love to find a way to just break that process within those gaps, rather than just, no one's going to be okay with removing decks. But I'd love to see if we could find a way to replace the process without fully replacing the decks. That's what we need to do, is in those gaps, something that's going to work. If we spaced it far apart, that would work, and then every high heel would fall through it. We'd have so many lawsuits. That's not going to work. So there's practical considerations. Yeah. And that's interesting about getting decks from homes being remodeled. Yeah, it's something we can do. In fact, we're just right now, we're just sort of doing a volunteer study with Marin County Fire. They're looking at mulch. California is really moving in that 0 to 5 foot zone, trying to figure out how to prevent. So they're trying to, there'll probably be some regulation about preventing materials being in that zone. And so Steve is part of that, and is kind of helping organize that. And we're probably going to have a bunch of mulch out for 6 months in Marin County, getting it aged as much as we can, and then run it back to the lab and test it, as well as doing some field testing. So, but even getting a spot that won't be messed with for 6 months is hard.
All right, we are running out of time, but we have maybe a couple of questions. I see Branko Kosovic raising a hand. Branko.
Hi, Michael. Thank you for a nice talk. Could you comment more about the balance between full physics modeling and data-driven modeling, considering the complexity of the problem and all the uncertainties when we attempt modeling?
Yeah, great question. I'm here in the Bay Area, and so I'm in the middle of data modeling central, and I am the first to criticize everyone who tells me they're going to go for a data-driven wildfire model. But I do think that some aspects of the problem may be better suited for some data-driven. You know, our department is even looking at the future for ME, and we'll probably have a search in the future for some data-driven, mechanical engineering or something. But I think the difference is that in engineering, the focus is not in the data-driven and how fancy your data-driven model is. I still think of data-driven as very nice multidimensional fits. The important part is that it's focused on physics. So like you link exposure from a semi-physical model to the damage. Like, so whatever you're fitting has to have a physical basis. Come on, coefficient of drag, these are all correlations, but they're based on a Reynolds number, they're based on that. And I know we're not at that sophisticated level, but I think we have to do our fits based on things that physically make sense. And if that's true, then we can start to scale those things up. I mean, and there's all these aspects we didn't understand. I didn't think as deeply on the multiple ignitions from earthquakes versus wildfires from spot fires. That's interesting. I don't know how that would affect some of these processes, but these are all things we have to keep investigating. I think there's still a huge role for, you know, just like there is in mechanical engineering, going from, you know, CFD with simplified models to doing DNS for certain problems. The same scale happens here. We would want a CFD of a wildfire through a community. This hasn't really happened, but this will learn a lot. But no firefighter will have that in their pocket, and no community designer will use it unless it's a really expensive community. Instead, we're going to have something quick and dirty that the communities use, and an expensive model that the universities use to update the quick and dirty model. I think that's the level it's probably going to be. And even in wildfire, everyone still uses a Rothermel-based model. I mean, Colorado, you know, moved toward the big CFD models, but I still haven't seen major improvements that have changed actions because of that. The biggest change in action has become data, just knowing where the fire is and knowing how the wind's changing is going to help the predictions. So for WUI, we probably need to know more and more about past data so that we can have a good validation data set, which doesn't exist right now.
Thank you.
All right, I'm sure we have more questions. I have a lot more questions, but maybe I can catch you in another separate one-on-one meeting, Michael. So with that, I'd like to thank you for the wonderful presentation, and I'd like to invite everyone to give you a remote applause. Thanks for spending your time with us today.
Thank you so much. And yeah, hope to be in touch with many of you in the future.
Yeah, so
thanks again for the invitation.
Yeah, so let me just stop the recording and